Ja, schönen guten Abend. Es freut mich ja sehr, dass Sie die Anstrengungen unternommen haben, hier in den 5. Stock hochzukommen, trotz des ausgefallenen Fahrstuhls. Ich habe gehört, einige Leute haben es gar nicht gemerkt, weil sie immer die Treppen nehmen, aber also mir ist es beim Reinkommen in das Gebäude nicht unentdeckt geblieben. Also umso mehr, da kommt tatsächlich auch noch jemand, herzlichen Dank für das schon erwiesene deutliche Interesse an dem Vortrag, dass die körperliche Anstrengung auf sich genommen wurde und überhaupt sich bei dem Wetter noch mal rauszubewegen. Ja? Also doppelte Bravo. Herzlichen Dank. Mein Name ist Stefan Neuers, ich bin stellvertretender Leiter vom Radgen Forschungslabor und begrüße Sie nochmal hier zu unserer Vortragsreihe Konservierungswissenschaften und Dialog in Kooperation mit unserem Förderverein, der hier auch anwesend ist. Also wenn Sie daran Interesse haben, sprechen Sie die Kollegen gerne an. Der Förderverein spendiert nachher auch immer noch mal Getränke am Ende des Vortrags. So, now I will switch to English because our speaker today is from quite far away. He certainly had to further struggle. Nobody made such an effort to come from Tokyo, but he did. He actually has a study stay in Paris, and so it was not so long way to come here to present here, just from Paris, but nevertheless. Hiroshi Wada studied chemistry, and after graduate school he changed to conservation science. He is since 2009 in the Tokyo National Museum, and since 2021 he is director, or he is head of Conservation Science Department. And he was already presenting last time about showcases and had very impressive pictures and images to illustrate the results. And today's lecture will be about transport, vibrations during transport, and I really look forward to see the nice generated images from you, Hiroshi Wada.
Thank you, thank you. Thank you for giving me the opportunity to speak at such a wonderful place today. I came to this same place last year. Do you all remember me? I came to Berlin again this year with my colleague, Mr. Yano. He is the chief designer of my museum. And I like to thank Christina and Stefan for preparing today's lecture, and my friend director Stefan, who is now studying in Canada, I believe. And important aspect of preventive conservation is to maintain the environment surrounding cultural properties, the museum environment, in a safe and stable condition. So, what exactly does the museum environment mean? The museum environment can be better understood by considering how cultural properties move with museum activities. Many cultural properties are stored in storage for long periods. Occasionally, they are moved to exhibition rooms, and after a certain exhibition period, they are returned to the storage. In essence, the movement of cultural properties with museum activities can be simplified as a back and forth between the storage and exhibition room. For example, the brown stains that appear on paintings are the result of extreme fluctuations in temperature and humidity within the storage environment. And additionally, excessive light from exhibition lighting can cause fading of dyes. Vibration and shocks generated during transportation can lead to structural damages. In other words, the causes of damages to cultural properties exists in their surrounding environments. The transportation environment here I will discuss today is one of these three environments. It is a very important environment. Regarding the improvement of the transportation environment, there are very few researchers in Japan. However, internationally, it is a field that has been gaining importance in recent years. However, there are significant challenges associated with the packing and transportation of cultural properties. In this diagram, the vertical axis represents either the strength of cultural property or the magnitude of the acceleration. If a cultural property can tolerate an acceleration up to A here, but the acceleration during transportation B exceeds A, the cultural property will theoretically be damaged. However, if packing increases the strength to C here, then theoretically the cultural property will not be damaged. The major challenge with packing and transporting cultural properties lies in the fact that there is no established method to estimate the strength A of cultural properties. Unlike industrial products, cultural properties cannot undergo drop or vibration tests, making it impossible to measure their strength non-destructively. As a result, packing inevitably becomes excessive, leading to higher costs. Additionally, packing techniques for cultural properties rely on traditional craftsmanship, which has yet to be scientifically evaluated. Currently, we are working on measuring the risks of acceleration that occur during the transportation of cultural properties. However, there are still many challenges that need to be addressed in the future. To summarize the challenges, one is how to scientifically evaluate packaging technology, and how to preserve traditional techniques, and how to know the fragility of cultural properties. To address these challenges, we plan to take the following approach. First, we will measure and evaluate the vibrations and shocks generated by vehicle. Next, we will investigate how packing materials for cultural properties respond to the vibrations and shocks. Finally, we will examine the responses of models made from the same materials as cultural properties or partial structural reproductions when subjected to vibrations and shocks during transportation. Our goal is to design the packaging and the transportation of cultural properties based on scientific evidence. To do this, we need to integrate information about three things: transport vehicles, packaging materials, and cultural properties. Today, as a case study, I will introduce the transportation of a famous Buddhist statue. The statue, known as Ashura, is a national treasure in Japan from the Nara period and is preserved at Kofukuji Temple in Nara Prefecture. As you can see, it has a highly complex shape with 6 slender arms. This subject involved transporting the statue approximately 480 kilometers from Nara to Tokyo National Museum for a special exhibition. Here is a packing plan we developed. There are two critical challenges. One is how to fix the statue to the box safety. And second is how to prevent from shock and vibration. To address these challenges, first, fix the 6 arms. so we developed special support tools. Second is vibration isolation. We used isolators. As a result, we designed a 3-layer packaging box consisting of an inside box, an isolation box, and outside box. This is an illustration showing an overview of the packaging design. The actual packing process was carried out in 2 steps. First, Ashura was securely fixed inside the inside box. The waist and legs of the statue were firmly stabilized, while the arms were secured using specially developed support tools. This ensured that Ashura became fully integrated with the inside box. Next came the second step. The isolation box and outside box were pre-assembled as a single unit. The inside box, now containing Ashura, was then fixed within this unit, completing the packing process. This is a photo of the inside box, and this is a photo of an isolation box and integrated with the outside box. Isolators are installed at the bottom. This is an illustration of the isolator. The isolator is a product by Anydyne and features a specialized structure with wire ropes. This is the installed state of the isolator. The choice of isolator depends on the load weight applied to each unit. This is how Ashura's waist and legs were secured. Usually, statues mounted on pedestals have tenons on the soles of their feet to fix them to the pedestal. This tenon was used to hold the feet in place. And this is a support tool we developed to secure Ashura's 6 arms. In fact, the cross-section of Ashura's arm is hollow. Each arm was first wrapped in soft paper tissues and then protected with urethane. And that the arms were supported by carved aluminum pieces shaped to match the surface of the arms, holding their position securely. To ensure positioning, the support tool allows adjustments in 3 directions. These are the arm support tools, including prototypes. This is the support tool temporarily installed in the inside box. Ashura's arm will rest on top of these support tools. The actual packing process proceeds as if assembling precision equipment. It is like a surgical operation. Since Ashura had 3 arms on each side, careful attention must be paid to the packing order. Furthermore, the arms intersect 3-dimensionally, making the structure within the inside box highly complex. This shows the complex arrangement of screws used to secure the position of the arm supports. And this is a rare video capturing the packing process. It shows the precise positioning of the arm supports. The location of the support basement is determined as you see the laser. using a laser. And marking the aluminum panel, and following this, aluminum panels are processed and drilled for fixing the basement, the support tools. Now they are fixing the support tools. They fix the position. Moment. Okay. Just a moment. Okay. This shows how detailed and complex the packing process is. Before transporting Ashura, we conducted experiments to evaluate whether this packing method was appropriate. After completing the production of the packing box, we placed a dummy weight inside the box instead of Ashura, loaded it onto a truck, and drove along a section of the highway intended for transportation. During the test run, we analyzed generated by the truck as well, analyzed the acceleration generated by the truck as well as the acceleration within the packing box. Based on the results, we made adjustments to the packing box design. In addition to the driving tests, we conducted vibration tests by securing the packing box to a large vibration simulator. Using the results from these experiments, we optimized the positions of the arm supports and isolators. This is the vibration testing process. Vibrations ranging from low to high frequencies are applied to the entire box. We examine how the box responds to each frequency and evaluate the most effective placement of the isolators for reducing vibrations. This is a scene during the transportation of Ashura from Nara to Tokyo. Based on the experimental results, dummy weights here were loaded onto the truck along with Ashura. During the actual transportation, we also measured the acceleration generated on the truck bed and inside the packing box. These are the comparisons of the acceleration data measuring during the experiment, left one, and the actual transportation, right one. The improvements made based on the experiments reflected in the reduction of acceleration during the actual transportation. This is a Ph.D. profile. Vertical axis shows the energy of the vibration, and horizontal axis shows the frequency. So it is evident that vibrations during the actual transportation were attenuated compared to those during the experiment. Through these efforts in packing and transportation, we successfully held the exhibition at the Tokyo National Museum. The exhibition was a great success, attracting over 800,000 visitors who had the opportunity to view Ashura up close. More than a decade, 10 years, has passed since this grand project, and technological advances have enabled measurements that were previously impossible. Additionally, with our accumulated experience in transportation measurement, we have gained a clearer understanding of the fundamental experiments we need to conduct. In the second half, I will introduce a recent case study on vibration measurement. When measuring vibrations during the transportation of cultural properties, we use acceleration data loggers, like here. The 4 key parameters in the measurement protocol are shown here. Sampling frequency, wake-up interval, signal trigger level, and frame size. In the past, due to the limited memory capacity of data loggers, we have to carefully optimize the settings to capture the overall characteristics of transportation. However, with the increased amount of memory available today, the need for fine-tuning has decreased. It is now possible to continuously record vibrations throughout the entire transportation process. But it is important to note that this approach significantly increases the data volume. We conducted continuous vibration measurements during transportation. I will now introduce a case study from these measurements. As shown here, this was a relatively long distance example of cultural property transportation in Japan. The transportation took 5 days and 4 nights using both trucks and ships. Tokyo is here, and this is Okinawa Prefecture. The transported cultural property was glass plate negatives, as shown here. Here is an overview of the measurement. The sampling frequency was set to 800 Hertz. We created a dummy box filled with weights matching the weight of the glass. Data loggers were installed both inside the dummy box and the truck bed. The total transportation time was 89 hours. Here is a setup of the data loggers in the dummy box and on the truck bed. Here is a packaging setup. First, the glass was wrapped in neutral paper, and this is storage boxes made of neutral paper, corrugated cardboard. And glass dry plates placed in a storage box. This is storage box, and cardboard for packing with foam material placed at the bottom, and wrap the preservation storage box with cotton wrapped in paper and set up. In fact, a large number of glass plate negatives were transported. They were located onto the truck which departed from Tokyo. Here is the data analysis process. Since the measurement was taken at 800 Hertz, the collected data became very large, reaching about 3.6 gigabytes in total size. Using the free software provided with the data logger, we converted the data into several split MATLAB format files. The files were split to avoid processing interruptions caused by the large data size. After that, I merged the split files vertically using code 1. Next, using code 2, I specified channels and time periods and performed Ph.D. calculations. Finally, with code 3, I visualized the data. While some manual operations were involved, the use of these codes enabled semi-automation of the analysis. As a result, even with a large volume of data, the analysis could be completed in a relatively short time. I will now explain some of the innovations we applied in this analysis. Ph.D. Fast Fourier transform analysis was necessary to decompose the vibration data into frequency components. In FFT analysis, the vibration data must be divided into predetermined frame sizes. In FFT analysis, a window function is applied at each frame to create a periodic pattern in the vibration. Therefore, the window function forces the vibration at the end of each frame to be weakened. The problem is that if important vibration information exists at the edges of the frame, it might be lost during this process. To solve this problem, overlap processing is used. Here is an overview of the overlap processing. In this time, I fixed the overlap rate at 90%. I carefully considered the section of the frame size. So after calculating the Ph.D. For each frame, the frame size was determined based on the appearance of the Ph.D. For example, with a frame size of 2 seconds, it appears as this. The top graph shows the time variation of the Ph.D. with frequency of the vertical axis. The bottom graph shows the time variation of the vibration with acceleration in g on the vertical axis. Let's see how the changes as we adjust the frame size. It becomes clear that there is a trade-off between time resolution and frequency resolution. It depends on the frame size. And after these experiments, we decided the frame size. Based on this examination, I conducted that the frame size of 7 seconds was appropriate. This decision was made because the balance between frequency resolution and time resolution appeared visually optimal, although it was not based on statistical analysis. Here is the data from the track bed, and here is the data from inside the box, dummy box. Here is a comparison over a short time interval. Please look at the section enclosed by the red dotted line here. Frequencies above 50 Hz were not present inside the box. Here is a comparison in the form of Ph.D. plots. It is clearly visible that the high frequency components inside the box are significantly lower. Here is a comparison with the averaged Ph.D. values for better clarity. It is evident that the high frequency components inside the box are smaller. On the other hand, a frequency around 10 Hz here were amplified inside the box compared to the track bed. Here is the Ph.D. in the box divided by the Ph.D. in the track bed. In other words, it shows the ratio of the vibration of the track bed and transmitted into the box at each frequency. Both figures have frequency on the horizontal axis and the transmission ratio on the vertical axis. The left figure uses a logarithmic scale for the vertical axis, and the right figure uses a linear scale. It is clear that the transmission ratio was high for frequency around 10 Hz. To confirm this phenomenon, we conducted experiments after the transportation. We replicated the same packing used during transportation. Packing box is being secured to the vibration table. And then input the sine wave from 2 Hz to 500 Hz and random waves. This random wave used international standards. Here are the experimental results. The left figure is experimental results. This is the result of an experiment using sine waves. And the figure on the right shows the measurements recorded during actual transport. It was confirmed that a resonant frequency exists around 10 Hz. We identified the resonant frequency of the box. It is important to note that these results represent the vibration response characteristics of entire box. Looking at the internal structure of the box, so many packing materials are used, making it not simple. The object here is placed inside a neutral paper box, and polyethylene sheet here is laid at the bottom of the neutral paper box. Furthermore, the neutral paper box is wrapped in cotton. It is not simply placed into a cardboard box. And the polyethylene foam is laid on the bottom of the cardboard box. Most of this packing design was created based on the experience of packing technicians. Ideally, the properties of each packing material used should be understood before designing the packing. However, when I joined this project, it was at the stage of initiating transportation measurements. As a result, this presentation follows a reverse order, verifying the outcomes after the transportation was completed. Therefore, experiments were conducted to understand the properties of each packing material used in the packing process. All of this was done after the transportation had been completed. So we tested polyethylene sheet and natural cotton and polyethylene foam. The polyethylene sheet has the highest vibration transmission rate around 100 Hz. And cotton has the highest vibration transmission rate around 5 Hz. And polyethylene foam has the highest vibration transmission rate around 40 to 50 Hz. Of course, these properties are known to depending on the load weight per unit area. And the magnitude of the acceleration of the vibrations as shown by previous studies. These results are based on applying the same weight as the transported glass plates. Here are the experimental results for the packing material used. The discussion of these results is still ongoing. I suppose that the resonant frequency of the entire box is determined by the combination of the individual vibration characteristics of each material. Here are the conclusions. We semi-automated the vibration data processing, and we optimized the frame size for vibration analysis, and we confirmed the characteristics of the box through vibration experiments. However, there are still significant challenges to address. It is essential to identify which types of vibrations the cultural property being transported is particularly sensitive to. I look forward to learning more from the research result you will share with me at this opportunity. So my presentation is that's all. Thank you for your attention. Thank you very much.
Yeah, thank you.
Yeah.
Well, that's a very nice talk about all the possibilities, how you can track the vibrations. Do we have questions from the audience?
Thank you very much for this thoroughly investigation of the behavior of the packing material and so on. So I think so you have to be sure just to get your specimens from one place to the other safely. So this is, I think it's an issue. What I just, first of all, mostly thinking of is just, I think the most essentially are all these power spectrum analyses. Mm-hmm. That's, and I wonder about not only the material, so that is the last, from the last what you told us to other points. So you have the dependency on the kind of material and the resonance frequency. But how about the shape of your body?
Yeah.
And every body, even our objects, they have an intrinsic frequency. And so just take a music instrument, you have only wood. But all we know how dependent is the intrinsic frequency on the shape of the instrument. So I think it just so we have investigated all the packing material, but how about a possible intrinsic frequency of your object, and how just if you change the shape of your specimens for packing materials. So do you have some correlation in this direction?
Yeah. Now I'm thinking about the using the 3D printer. So because we usually use the commercial product for the packing materials, so we only can buy the packing material. But using a 3D printer, we can make the optimized packing material for each object. So it's my idea, but it is possible or impossible, I don't know. So the structure of the packing material is very important. for the influenced for the natural frequency of the packing material, I think. Yeah. So I want to make the individual packing material. So it's my thinking, researching plan.
You did make something very particular. I mean, for the Ashura, for the first example, it was very
supporting tool.
Yeah,
yeah.
Supporting tool was not printed, but it was adjusted at least very minutely to the object. For doing so, did you have a 3D scan or from the object to start with already?
No, not yet. So in this Ashura's case study, more than 15, what time? More than 10 years, 15 years ago, maybe. So the 3D scanner or 3D printer, there no exist in this world. But now we can easy to get the three-dimensional information of the object. So I want to try the apply such a 3D devices, but not yet. Yeah.
You showed us two examples of packaging designs. So one was with very not so many contact points to the artifact. So the Ashura only had a few points where it was fixed inside the transportation box. And then the other example, the glass plates, you had an overall wrapping of the artifact. Which one was, do you think, more appropriate? Is there a clear favorite, or does it depend on the shape of the artifact or maybe the material?
So I think shape of the object is very influenced the vibration characteristics. Yeah, and
Yes.
yeah.
I think for the Ashura statue, it's very difficult to design something which is really encompassing it completely, no? Or would you be willing to do something which really, I mean, mechanically it would be very challenging, no, wouldn't it?
Sensitive to wrapping it.
Yeah.
I think it was also some polychromy partly on it, so you would have perhaps some fragment of the packing in that case.
Yeah, we're interested whether the data shows a clear, if it's if it buffers more vibration if you wrap it completely, or if you have fewer contact points than the
well, perhaps to pose this question slightly differently, but would the Ashura have benefited from a better packing if you would have more contact points to fix it?
Yeah, I think so. But the shape is very, very complex. So there are no space to fix the arms. So it is enough to fix one arms. Each arm is fixed with two points. So we didn't have other methods to fix these 6 arms.
Yeah. Just directly to this point, I think this is a very important issue, because when you just try to fix the arms to prevent it breaking away during the transport on one side, but with each connector you do have a perfect coupler of any frequency. So that you're just doing quite the opposite, just when you fix it stiffly, and so you have then the problem just to prevent a vibration coupling from the outside to the object. So this is, I think, the problem you are addressing, isn't it?
I'm not sure I was able to follow what you mean.
So our purpose is Ashura must be fixed with inside the box. And so that's why we use the wire rope isolator, because we don't know the natural frequency of the Ashura. So if the Ashura was completely fixed, the inside the box, we only focused on the reducing the vibration of the track is enough. So, but the fixing of the Ashura is completely or not completely. I don't know. Maybe it is not enough to fix the Ashura in the inside box. Maybe or it's enough. Yeah. Yeah.
Any more questions? I was just imagining with the Ashura, it seemed to go many man-hours, many work into this fixation and construction of this. I don't think that you can. I mean, you said it's a national treasure, so it's a very unique object. But sometimes, if you have exhibitions, there are several objects which have to be transported. So, would there also be a more easy way you would propose for something like the Ashura if you would have less resources to spend on a good packing?
Yeah, this case study is very, very special case study. And, I don't want to this project again. It's very highly, it's very risky.
So next time just wrap it in some foam, then it's good.
I have a question there. Influence of the direction of the movement to this object, because I think if I would pack it, maybe you recommend one direction for the transportation. You can't really measure them because it's just the acceleration of the truck itself.
Yeah, you mean the transportation direction of this statue? Yeah, because this statue exists the standing shape. So I think it can resist against the vertical acceleration is the the best resistance it has against the vertical acceleration. So we transport this statue. Don't something like don't do this direction and the standing keep standing direction and transport. Yeah.
Just a completely different question about the liability. So the transporting companies normally, how much have they a certain responsibility on anything that could harm your object? So is it just some shared responsibility, or have the transporters have to take care and also to provide the knowledge for that? Do they?
Yeah. That's an important thing, I think. Yeah.
Okay, no, one further question?
Sorry.
Yeah. Okay.
For the first case study, you used mainly metals to construct the case, and in the second, you used a mixture of flexible materials like foam.
Yeah.
And cotton, which is like slightly bouncy, but maybe not doesn't spring back as much as like a foam. How did it influence the vibration? So did you find the metal is easily transporting it, or does it cancel it?
I think the metal has a high frequency. Metal has a high frequency. The natural frequency of metal is very high, and soft material is very low. Has a low frequency, but the Ashura's isolation box and packing box is made by the aluminum because we want to make a very tight packing box because we use a wire rope isolator, so we can determine the natural frequency. We can control the frequency of the entire box with wire rope. So we made a box using the metal, but second case study. In fact, I did not join the design of the packing box. They already made, and I only to measure the transportation. And after the transportation, I conducted experiments. But the second case study, this object is also important cultural property, but the transport company has a lot of experience transport like this object, so they already has a custom to made a box with these corrugated cardboard boxes. Through the many experience, they didn't have some accident, so that's why they select these materials. Yeah.
So basically, it comes back to experience. Any more questions? If that's not the case in the moment, perhaps after a glass there will be the idea for another question. I don't know. Yeah. Thank you again for all the discussion and information and this very wonderful presentation. Thank you.
Thank you.